Hi folks, for this last video of 3.4, we're going to work through some work energy example problems. There's just two here. We'll do a lot more in class for this topic. So first one we have is flat ground. So you can pause and read, or you already read it. Block of ice sliding along ground that has a rough patch. So like any energy problem, I'm going to label it in terms of the types of energy that I see. Now this is flat ground, meaning this block never changes height, so I'm not going to consider gravitational potential energy here. I am going to consider that there's kinetic energy here and kinetic energy here. Those should be different because of the rough patch. This rough patch is going to exert a force of friction, and this is when there is work done by a non-conservative force. So I can write the equation that describes this. I can say that the kinetic energy at the beginning plus the total work done by non-conservative forces is equal to the kinetic energy at the end after it's passed the rough patch. Now, because I'm doing work, I want to know the direction that things act. And so this block has, while it's on the rough patch, it has three forces acting on it. Normal force, gravity force, and friction force. The friction force is the one I'm concerned with, and if I add to this picture the direction that the block is moving, I get a picture of the angle between the friction force and the direction of motion. And so that's pretty clearly a 180-degree angle. So now I can move into solving the problem because I know what my angle is going to be and I have all the other information given. But the important part of this problem really was identifying that there's a change in kinetic energy because there's work done by friction. So now I write out all the equations. I won't always write out equations, but in this case, I do need all three equations. Now there's no variable that I can cancel here because there's no variable that is in common between all three terms in this equation. So I'm going to need every value that I have up above to plug in. So I'm going to spread out here. 1/2 times the 0.6 kilograms times 4.5 meters per second. That gets squared. The force of friction is 1.2 newtons. The rough patch is 4 meters long. And then again, I'm going to use 180 for the angle because the displacement is to the right, but the force of friction is to the left. On the right-hand side of the equal sign, I have 1/2 times 0.6 times the final speed squared. So that's like all of my data put in there, and then I'm just going to calculate. So this first term is equal to 6.075. This second term is equal to negative 4.8, and this far right term is equal to 0.3 v squared. So if I combine these two, divide by 0.3, take the square root, I get a final speed of 2.1 meters per second. Now you should always check your answer, right? It should be like intuitively right. If it had a speed of 4.5 meters per second and then it encountered a rough patch, it should have slowed down. And so 2.1 meters per second being smaller is probably right. Okay. Next question has to do with a block sliding along a flat surface and then down an incline, and then we're looking at the speed at the bottom of the incline. So again, I'm going to analyze this in terms of energy. Now the block starts at a height and ends at the bottom of that height. So over here, it's going to have kinetic and gravitational. That's at the beginning. This rough patch, it says the rough incline does negative 15 joules of work on the block. So this is where there's work done by non-conservative forces. And then when it gets down to the bottom, there's no more potential energy. It's only kinetic. So I can now write an equation summarizing that. Okay, so I have the initial kinetic energy plus the initial gravitational energy plus the total work done by non-conservative forces equals the final kinetic energy. Okay, so that one has 4 terms, whereas I had 3. And I want, careful reading pays off. It says that the work done by the rough incline is negative 15 joules. So if I already know how much work is done by the incline and I want to find speed, I don't need to write out FD cosine theta. So I'm going to write out everything else, but I'm going to leave the non-conservative work as just its own single variable because I know the value of it. All right, so now I have to calculate, and that's going to be V naught. I have to calculate the speed. I'm going to plug in all of my values. So I'm going to go 1/2 times the mass is 2 kilograms, and the initial speed is 3 meters per second. That gets squared. Gravitational potential energy is next. So 2 is the mass, 10 is going to be my value of g, and then 2 is the height of the incline. Backtrack just a moment. I was not able to cancel any variables. Mass does appear in 3 of the terms, but not in all 4. Only if it's in every term can I cancel it. All right, so I have kinetic, I have gravitational potential. The work done by friction is negative 15 joules. So I'm just going to put negative 15 in there. And then 1/2 times the mass of 2 times the final speed squared. Okay, so this is I'm gonna put in some, I'm gonna calculate each value. This first term is 9. The second term is 40. This is still negative 15. 1/2 times 2, that does cancel to 1, and that's equal to v squared. So 9 plus 40 is 49, minus 15 is 34, and then I take the square root. This final speed is 5.8 meters per second. Okay, now this does present itself with an opportunity for like a conceptual understanding here. This final speed is greater than the initial speed. But when you have non-conservative work, that doesn't have to happen, right? Acceptable answers for this include anything from 0 up to 7 meters per second, right? If there is no non-conservative work done, then the total energy was 49 joules, and the square root of that would be 7. So if I got an answer that's greater than 7, there's a problem. The more work is done, the lower this value of V would be. If this value of non-conservative work is equal to 40, then the final speed would be 3, which basically means that the incline took out enough energy to offset the effect of gravitational potential energy. And then the maximum amount of non-conservative work this incline could do would actually be 49 joules. And at the bottom of the incline, the block would just come to rest because all of its energy had been taken away. So the fact that this is larger than 3 meters per second is not a problem. There's lots of opportunities for varied answers there.